54 years ago, in December 1972, the last human left a footprint of his boot in the gray, merciless dust of the lunar regolith. When Eugene Cernan climbed the stairs of the Apollo 17 lunar module, he spoke words about hope and peace for all humanity. At that time, it seemed that the moon was only the first step, and within decades, our cities would bloom on the red sands of Mars. However, reality turned out to be much harsher. Budgets were cut, political interests shifted, and the majestic Saturn V rockets became museum exhibits, gathering dust under glass covers. Humanity, frightened by its own boldness, retreated to low Earth orbit, closing itself in the safe cocoon of the International Space Station, where Earth is always nearby, only 400 kilometers beneath one's feet. But today, in 2026, the silence of the great cosmos will finally be broken. We stand on the threshold of an event that will either become the greatest triumph of the 21st century or the loudest tragedy in the history of space exploration. The Artemis II mission, 4 people, Commander Reed Wiseman, pilot Victor Glover, and mission specialists Christina Koch and Jeremy Hansen, are preparing to challenge the void that we have not visited for more than half a century. Why does this flight cause such trepidation in the hearts of engineers at the National Aeronautics and Space Administration? Why do experienced veterans of spaceflight whisper that Artemis II is the most risky mission since the first landing of Neil Armstrong? The answer lies not in the romance of the stars, but in the cold, relentless statistics and technical reports that we will analyze down to the last comma today. We are used to thinking that modern technologies automatically make space safer. We have supercomputers in our pockets that are more powerful than all the computing centers of the 60s combined. We use artificial intelligence for trajectory calculations and the latest composite materials for ship plating. However, the physics of space has not changed. The gravitational well of Earth is still as deep, the Van Allen radiation belts are still as deadly, and the temperature upon atmospheric entry is still capable of turning any metal into molten vapor. In this documentary study, we will not speak in general phrases about the striving for the stars. We will dive into thousands of pages of official reports from the Inspector General of the National Aeronautics and Space Administration. We will examine data obtained during the uncrewed test of Artemis I, where the heat shield of the Orion spacecraft behaved completely differently than predicted by the most advanced computer models. We will break down in detail the architecture of the Space Launch System, a rocket that is a true engineering monster, combining the space shuttle technologies of the last century and the digital innovations of today. We will ask uncomfortable questions. Why did the National Aeronautics and Space Administration decide to send people on a ship whose critical life support systems have never been tested in real flight conditions to the moon? How will cosmic radiation affect the cognitive abilities of the crew during passage through zones of the highest intensity? And what will happen if the main engine of the European service module fails at the moment when the ship is behind the far side of the moon, in a zone of total radio silence? This is not just a story about technology. It is a story about 4 brave individuals who agreed to become subjects in the largest biological and technical experiment of our era. We will consider the positions of leading astrophysicists, scientific publications in the journals Nature and Science, as well as reports from the European Space Agency and the Japan Aerospace Exploration Agency. Today we open the curtain over the real Artemis II. Without censorship, without patriotic slogans, only naked science and the mathematics of risk. Why could this path to the moon become a one-way road? And why, despite all warnings, must we still fly? Welcome to the world of high science and extreme testing. This is a story about how humanity once again dared to step over the threshold of a safe home and go out into an ocean where there are no shores. To truly comprehend the degree of risk of the Artemis II mission, we must take a journey into the past and understand one of the most fascinating and simultaneously disturbing paradoxes of modern science. This is a question often asked by skeptics. If we were able to send people to the moon using the technologies of the 70s of the last century, why does it cause such difficulties now, in the age of artificial intelligence and quantum computing? The answer lies not in a deficit of computing power, but in the deep systemic degradation of specific industrial knowledge, which researchers call lost technological heritage. the phenomenon of lost knowledge and the myth of blueprints. There is a common legend that the blueprints of the legendary Saturn V rocket, which carried Neil Armstrong and Buzz Aldrin to lunar orbit, were lost or destroyed. This is not quite true. The archives of the National Aeronautics and Space Administration store thousands of microfilms and digital copies of documentation. However, the problem is that a rocket is not just a set of blueprints. It is a living ecosystem of production. In the 60s of the 20th century, over 400,000 people and about 20,000 separate companies worked on the Apollo program. Many of these enterprises have long gone bankrupt, changed their profile, or were absorbed by corporate giants. Metal alloys, methods of chemical etching for tanks, specific processes for welding aluminum, all of this was a product of its era. When production lines were stopped after 1972, what sociologists of science call tacit knowledge began to disappear along with the generation of engineers who were retiring. You cannot simply give a modern factory a blueprint for a valve from 50 years ago because the machines that manufactured it no longer exist, and the standards for material purity have changed radically. Attempting to recreate Apollo today would cost more than creating a new system from scratch. That is why Artemis 2 is forced to go a different way, the way of reverse engineering and adaptation. The Space Launch System rocket uses engines from the Space Shuttle program, but their integration into a new architecture proved much more complex than expected. We are trying to combine the analog reliability of the past with the digital precision of today, and this hybrid approach creates unique failure points that did not exist 50 years ago. Change in the safety paradigm. Desperation versus mathematics. Another important aspect of the historical context is the cardinal change in the culture of risk. The Apollo program was a child of the Cold War. It was a race for the survival of ideologies where speed was more important than absolute safety. According to modern aerospace safety experts, if the Apollo series missions were evaluated by today's standards, their probability of success would be recognized as unacceptably low. For example, during the flight of Apollo 11, there were more than 180 single points of failure, critical elements whose breakdown would mean the immediate death of the crew without any chance of rescue. Today, the National Aeronautics and Space Administration works under completely different protocols. The requirement for the Artemis 2 mission is that the probability of loss of crew should be minimal, less than one case per 300 flights. This forces engineers to create complex redundancy systems. But here an engineering trap arises. The more complex a system is, the more potential software errors and non-obvious interconnections it contains. We have moved from testing to destruction, which Wernher von Braun was engaged in, to model-based systems engineering. However, as shown by the history of the Orion heat shield in the first uncrewed mission, digital models are not always able to predict the chaotic behavior of incandescent plasma. The historical risk of Artemis 2 is that we are trying to be as cautious as possible in an environment that by its nature does not forgive any caution unless it is backed by real flight experience. New geopolitical architecture, the world against the moon. Unlike Apollo, which was a purely American project, the Artemis 2 mission is the pinnacle of international diplomacy and cooperation. It is no longer a race between two superpowers, but the creation of a global infrastructure. The Artemis Accords have united over 30 countries around the idea of peaceful lunar exploration. The European Space Agency plays the role of the respiratory system of the mission. Their service module is critically important for the survival of the astronauts. This is a huge diplomatic and technical risk. If the European component does not work, the American ship will be left without energy and air. This requires perfect synchronization of standards between continents. The Canadian Space Agency provides an intellectual advantage through robotics. The participation of Canadian astronaut Jeremy Hansen in the crew is a recognition of the contribution of Canada to the creation of the future Gateway Station. The Japan Aerospace Exploration Agency focuses on logistics and future presence on the surface. However, this international structure creates a new vulnerability. In the times of Apollo, the decision-making chain was short and vertical. Today, any political turbulence on Earth, from trade wars to budget cuts in partner countries, can affect the technical readiness of the mission. We are at a unique historical point. Humanity is returning to the moon not because it is easy, and not only because it is prestigious. We are returning because the moon has become the eighth continent of Earth, a source of resources and a bridgehead for a leap to Mars. But this turn toward deep space occurs against the background of the lost skills of the past and the excessive complexity of the modern world. It is precisely this gap between how we did it once and how we are forced to do it now that makes Artemis 2 the riskiest adventure of our generation. To understand the true scale of the risk of the Artemis 2 mission, we must focus our attention on the object towering over Launch Pad 39B at the Kennedy Space Center. This is the Space Launch System, a colossal creation of engineering thought 98 meters high, weighing more than 2,600 tons when fueled. It is not just a rocket, it is the most energy-dense construction that humanity has ever tried to harness for crewed flights. But it is in its architecture that the fundamental conflict between the proven past and the uncertain future is embedded. The heart of the beast, RS-25 engines, and the shuttle legacy. At the base of the central stage of the Space Launch System are four RS-25 engines. These units are true veterans of space. They were developed for the Space Shuttle program and are considered among the most efficient and reliable liquid rocket engines in the world. However, the first major risk lies here. The engines that will carry the Artemis 2 crew are not new products. They are actually the same engines that have already flown into space dozens of times. For example, engine number 2047 was previously used in 15 different space shuttle missions. Engineers at the Marshall Space Flight Center faced an incredible challenge: how to make technology from the 70s of the last century work in completely new modes. For Artemis, these engines were modernized. New control units, often called the brain of the engine, were installed and insulation was strengthened. But the main difference is that they must now operate at 109% of their nominal power for 8.5 minutes continuously. In the shuttle program, engines returned to Earth, underwent thorough inspection and repair. In the Artemis 2 mission, they will become expendable. Any microcrack caused by metal fatigue during previous launches decades ago could become critical under the pressure of ultra-high temperatures and vibrations. We are staking the lives of 4 people on the hope that these metal veterans will withstand the last, most difficult dance in their history: white giants, solid rocket boosters, and the point of no return. On both sides of the orange central stage are 2 5-segment solid rocket boosters. These are the largest and most powerful solid rocket engines ever created for flight. Each of them burns 6 tons of fuel per second, creating thrust equal to the power of 14 Boeing 747 aircraft at takeoff. Together, they provide over 75% of all rocket thrust in the first 2 minutes of flight. The physics of solid rocket boosters is relentless. Unlike liquid engines, which can be turned off by simply closing a valve, a solid rocket booster is actually a giant pyrotechnic rocket. Once ignition has occurred, it is impossible to stop. It will burn until all fuel is exhausted. This creates a situation that pilots call a ride on a fire tiger. If an anomaly arises during the first 120 seconds of flight, for example, a burn-through of a seam between segments, as happened in the Challenger tragedy, the crew will not have the opportunity to simply turn off the engines. The only chance for rescue would be the activation of the launch abort system, which must literally shoot the capsule with astronauts away from the exploding rocket. For Artemis 2, these boosters were lengthened by 1 segment compared to those used in the shuttles, which creates new dynamic loads on the entire rocket structure that have so far only been tested with humans in computer simulations. The fuel ghost, the problem of liquid hydrogen. The biggest headache for engineers of the National Aeronautics and Space Administration remains the fuel. The central stage is filled with 2 million liters of liquid hydrogen and liquid oxygen. Liquid hydrogen is the fuel of the future, but it has a terrible character. Its temperature is minus 253 degrees Celsius, which is only 20 degrees above absolute zero. At this temperature, most metals become brittle like glass. The hydrogen molecule is the smallest in the universe. It is capable of penetrating through microscopic pores in seals and welds. We saw this during preparations for the Artemis 1 mission in 2022, when the launch was delayed several times due to imperceptible leaks. For an uncrewed ship, this was only a technical delay. But imagine the Artemis 2 crew sitting in the cabin at a height of a 30-story building. They are strapped into their seats, Life support systems are running, and beneath them is a giant barrel of liquid hydrogen that is starting to leak. Any spark from static electricity could lead to a catastrophic volumetric explosion. The complexity of refueling and maintaining the thermal regime makes every minute before launch an act of balancing on the edge of a foul. Vibration resonance, the pogo effect in structural integrity. Another scientific mystery that concerns aerophysicists is the so-called pogo oscillations. This is a resonance phenomenon where pressure fluctuations in the combustion chambers of the engines coincide with the natural vibration frequency of the rocket body. The rocket begins to compress and stretch along its axis like a giant spring. In the 60s, during Saturn V flights, these vibrations were so strong that astronauts sometimes lost the ability to see instruments because of their heads shaking. For the Space Launch System, which is significantly longer and thinner than Saturn, this effect could be even more destructive. Experts in structural dynamics, in reports for the National Academy of Sciences of the United States of America, point out that the combination of 4 liquid engines and 2 powerful solid boosters creates an incredibly complex acoustic picture. These sound waves are of such power that they can literally shake the electronics inside the Orion ship. During the launch of Artemis 1, the power of the sound pressure was so high that it damaged part of the ground structures of the launch complex. How will this affect human internal organs and sensitive navigation instruments in the Artemis 2 mission? We will find out in real time. We must understand, the Space Launch System is a machine built at the limit of the physical capabilities of materials. It consists of millions of parts that must work in absolute synchrony. For the Artemis 2 mission, this test becomes critical because it is the first time this fire chariot is entrusted to humans. The risk is not just present, it is part of the rocket design itself. Every second of ascent through the atmosphere of Earth will be a struggle between engineering calculation and the chaotic force of released chemical energy. If the rocket is the muscles of the mission, then the Orion spacecraft is its brain, nervous system, and the only thin shell that protects fragile human life from the merciless vacuum. The development of this apparatus lasted over 2 decades, passing through 3 different presidential administrations and numerous changes in concepts. However, today Orion is the pinnacle of aerospace engineering of the 21st century. But it is in this perfection that a paradox lies. The more complex a system becomes, the more invisible failure points appear in it that cannot be predicted in terrestrial laboratories. Anatomy of the capsule. Space and digital vulnerability. The first thing that is striking when comparing Orion with the Apollo command module is its internal volume. If the Apollo cabin was like the cramped interior of a small car where 3 astronauts could barely stretch their legs, the pressurized volume of Orion is approximately 9 cubic meters. This is 50% more than its predecessor. This allows a crew of 4 not just to sit in seats, but also to perform complex scientific manipulations and even engage in physical exercises, which is critically important for maintaining muscle tone in weightlessness. However, behind this comfort stands unprecedented digital complexity. Orion is controlled entirely by a digital glass cockpit with 3 large liquid crystal displays and 60 physical switches. The software of the ship contains over 2 million lines of code. For comparison, the Apollo onboard computer had only a few dozen kilobytes of memory. The risk here lies in a phenomenon that scientists call digital fragility. In deep space, beyond the protective magnetosphere of Earth, electronic components are subjected to constant bombardment by heavy ions and galactic cosmic rays. According to research published in the journal Science, such particles can cause single-event upsets, when one bit in the computer memory instantly changes its value from 0 to 1. If such a failure occurs in a critical algorithm for engine control during braking near the moon, the consequences will be catastrophic. Although the National Aeronautics and Space Administration uses doubly and triply redundant systems, full dependence on digital code makes Orion vulnerable to software ghosts that may manifest only in real radiation conditions. European Service Module, the heart beating in time with the European Space Agency. Located beneath the conical capsule is the European Service Module, developed by the Airbus company at the request of the European Space Agency. This is a unique example of international trust. For the first time in the history of the United States of America, a critically important life support and energy supply system for a crewed mission to the moon was manufactured outside the country. The service module is a true power plant and resource warehouse. It contains 4 solar arrays with a span of 19 meters, which generate enough energy to power 2 ordinary houses on Earth. In addition, the European service module carries 8,600 kilograms of fuel for the main engine and 32 maneuvering engines, 240 kilograms of oxygen and 90 kilograms of nitrogen to create a breathable atmosphere, 730 liters of drinking water, which should be enough for 21 days of flight. The risk of this architecture lies in its inseparability. The command module and the service module are connected by thousands of wires, pipes, and sensors. Any microcrack in the cooling system of the service module will cause the command module to overheat in a matter of hours. Furthermore, the main engine of Orion is a repurposed engine from the Space Shuttle Orbital Maneuvering System, AJ-10-190. Although it is considered very reliable, it does not have a backup. If this single engine fails at the point of maximum distance from Earth, the crew will not be able to correct the trajectory for atmospheric entry. Life support systems, the struggle for every breath. On board Orion, humans will be in a closed loop. It is a microscopic biosphere where every breath of an astronaut must be recycled. The air regeneration system on Orion uses amino-functional polymer technology to absorb carbon dioxide. The problem is that on the International Space Station, similar systems occupy huge racks and are serviced by regular cargo ships. On Orion, everything must work perfectly in miniature. The dust and moisture cause particular concern for scientists. In weightlessness, any drop of sweat or microscopic skin flake becomes a potential threat. They can enter the ventilation system and block smoke sensors or air purification filters. According to internal reports from the European Space Agency, during the testing of ground prototypes of the system, difficulties arose in maintaining a stable humidity level. If humidity rises above 80%, it will lead to the formation of condensate on cold surfaces behind instrument panels, which threatens short circuits in complex electronics. Thermal challenge. Hell and ice behind one wall. A spacecraft in flight to the moon constantly rotates. This is the so-called passive thermal control mode, or barbecue mode. This is necessary so that the sun does not overheat one side of the ship to 121 degrees Celsius, while the other side freezes at minus 157 degrees in the shadow. The active thermal control system uses loops with liquid coolant that pass through the cabin walls and radiators on the service module. If the pump that circulates this coolant stops, the temperature inside the cabin will start to rise at a rate of half a degree per minute. The astronauts have mere minutes for repair before the equipment begins to shut down from overheating. We must understand that Orion is not just transport. It is the only shelter in an 800,000-kilometer journey. Its complexity is its main weapon against space, but it is also its vulnerable spot. Every bolt, every sealed seam, and every line of software code must be perfect. Because in deep space, Orion is all that separates a human from eternal oblivion in the cold void. We are approaching the most intense and technically controversial moment of the entire Artemis program. If a rocket launch is a demonstration of pure power and flight in deep space is a test of endurance, then returning to Earth is an act of desperate struggle with the very physics of the universe. When the Orion spacecraft approaches our planet, it does not just fall. It slams into the atmosphere at a speed of 11,100 meters per second. This is approximately 40,000 kilometers per hour. At such a speed, air stops being a transparent gas. It turns into an impenetrable wall that offers incredible resistance. Physics of the plasma hell, when air becomes fire. At the edge of the atmosphere, at an altitude of about 120 kilometers, the kinetic energy of the ship begins to turn into thermal energy. A detached shock wave forms in front of the blunt part of the capsule. The temperature of the plasma around Orion instantly jumps to 2,760 degrees Celsius. This is a temperature at which most metals we know do not just melt, but evaporate. To protect the crew, engineers at the National Aeronautics and Space Administration use the largest heat shield ever created for crewed vehicles. Its diameter is 5 meters. It is covered with a special ablative material called AVCoat. This is an epoxy resin with the addition of quartz fibers, which was invented back in the era of Apollo. Its principle of action is self-sacrifice. The material of the shield is designed to char and gradually peel off, carrying away colossal thermal energy and preventing it from penetrating inside the titanium frame of the capsule. The mystery of Artemis 1, unpredictable erosion. However, here we face a problem that makes leading scientists of the aerospace industry hold their breath. After the completion of the uncrewed mission Artemis 1 in December 2022, when the capsule was recovered from the waters of the Pacific Ocean, engineers discovered an anomaly that no one could have predicted. The heat shield did not look as expected. Instead of uniform and smooth burning of the material, specialists saw chipped areas and entire cavities. The AVCoat material was breaking off in large chunks, leaving behind an uneven surface. In the official report from the Office of the Inspector General under the number IG-24-011, published in May 2024, it is clearly stated, the heat shield exhibited anomalous erosion that was not observed during ground testing in plasma tubes. This caused a real storm in the scientific community. Why did the computer models, on which billions of dollars were spent, make a mistake? It turned out that the dynamics of the plasma flow around such a large object as Orion are much more complex than previously thought. Articles in the journal Nature suggest that microscopic air bubbles that get into the resin during the manufacture of the shield explode under the influence of extreme pressure and temperature, tearing off pieces of the protective layer. Risk to the crew, the burn-through scenario. For the Artemis 2 mission, where people will be inside the capsule, this anomaly is critical. If a piece of ablative material breaks off too early, it could lead to a change in the aerodynamic characteristics of the ship. Orion could start to spin or change the angle of entry into the atmosphere. But the most frightening thing is the so-called local overheating. If a deep cavity forms in the shield, the plasma flow can begin to act like a gas cutter, burning through the internal structure of the ship. Why did the National Aeronautics and Space Administration decide to fly without changing the shield design? Because a complete modernization of the shield would require the development of a new chemical formula for AVCoat and additional years of testing, which would effectively stop the Artemis program for a decade. Instead, engineers decided to rely on a margin of safety. They claim that even accounting for the chips, the thickness of the shield remains sufficient to protect the crew. However, many experts, particularly from the European Space Agency, express cautious skepticism. Can we be sure that in the next flight the erosion will not be even more aggressive? Skip re-entry. Ballet on the edge of catastrophe. Another risk factor is the new landing methodology known as skip re-entry. Unlike Apollo, which entered the atmosphere once and for all, Orion first dips into the upper layers of air to shed some speed, and then, using its aerodynamic shape, jumps up again, returning briefly to space. This allows the ship to fly a greater distance and land more accurately at a designated location near the coast of California. From a scientific point of view, this is a masterpiece of ballistics. But from the point of view of loads on the heat shield, it is a double trial. The shield is subjected to thermal shock twice. The first entry heats it up. Then in the cold of space, the material is subjected to thermal stress. And during the second entry, it must again withstand thousands of degrees. Any microcrack that arose during the first jump could turn into a fatal fissure during the second. Section conclusion, the price of confidence. We must understand that the Orion heat shield is not just a passive piece of plastic. It is a complex chemical laboratory operating in extreme modes. Scientific debates regarding the reliability of this unit continue today. Reports from the National Academy of Sciences indicate that we still do not fully understand the physics of the behavior of ablative materials at such large shield diameters. For the 4 astronauts of the Artemis 2 mission, these technical disputes will become reality in the last hour of their flight. When they see the bright orange glow of plasma in the portholes, they will know that their lives depend on the ability of a few centimeters of resin and quartz to withstand the wrath of the universe. This is the real edge of scientific progress, where calculations end and pure risk begins. When we look at the Orion spacecraft, we see a triumph of engineering. Titanium, aluminum, complex polymers, and millions of lines of code. But inside this high-tech shell is the most vulnerable element of the entire mission: the human body. The four astronauts of the Artemis II mission are biological beings who evolved over millions of years under the protection of a thick atmosphere and the powerful magnetic field of Earth. Stepping beyond this protective cocoon is not just a journey in space, it is entry into a zone of aggressive physics where the very fabric of life is subjected to constant destruction. Van Allen belts, the first circle of radiation hell. The risk begins just a few hours after launch. At an altitude of 1,000 to 60,000 kilometers above the surface of Earth are the Van Allen radiation belts. These are giant zones in the shape of toroids where the magnetic field of our planet catches and holds a stream of high-energy particles of the solar wind, mainly protons and electrons. In the Apollo missions, astronauts flew through these belts as quickly as possible to minimize the radiation dose. However, Artemis II has a fundamentally different flight profile. Since this is the first crewed test of a new system, the Orion ship will spend a significant amount of time in high Earth orbit to check all life support systems before giving the final impulse toward the moon. This means the crew will be exposed to radiation from the Van Allen belt longer than any other group of people in history. Scientific studies published in the journal Nature indicate that passage through these zones initiates a cascade of damage in cells. High-energy protons act like microscopic projectiles piercing the body. When such a particle hits the cell nucleus, it causes double-strand breaks in the deoxyribonucleic acid. Although our body has complex repair mechanisms, under conditions of high radiation intensity, these mechanisms begin to make mistakes, leading to mutations or programmed cell death. Galactic cosmic rays, the heavy artillery of the universe. As soon as Orion leaves the magnetosphere of Earth, it will find itself in the zone of galactic cosmic rays. This is a completely different level of threat. These are the nuclei of heavy elements, iron, magnesium, silicon, that were accelerated to relativistic speeds by supernova explosions in distant corners of the galaxy. The problem is that it is practically impossible to protect against galactic cosmic rays in a passive way. When such a heavy particle hits the aluminum skin of the ship, a process occurs that physicists call spallation or nuclear fragmentation. A secondary stream of neutrons and other particles is formed, which scatters inside the cabin like shrapnel from an explosion. According to reports from the European Space Agency, secondary radiation inside the ship can be even more dangerous than the primary one, as its biological effectiveness regarding the destruction of brain tissues and the nervous system is extremely high. Solar storms, a radiation shelter in the center of the cabin. In addition to the constant background, there is the threat of solar proton events, sudden flares on the sun that eject colossal volumes of radiation into space. If such a flare occurs during the flight of Artemis II, the astronauts will have only 30 to 60 minutes to prepare for the impact. Since Orion does not have lead shielding, it would be too heavy for launch. Engineers at the National Aeronautics and Space Administration developed an improvised radiation shelter. The astronauts are ordered to move water supplies, food packages, and even waste containers to the center of the cabin and hide behind them. Material rich in hydrogen, which water is, best absorbs the energy of protons. This is a survival situation on the edge of a foul. 4 people, squeezed between bags of water in the cramped space, wait for the solar storm to subside, knowing that every minute spent outside the shelter could be fatal for their immune system. Neurobiological risks, effects on mind and memory. Recent studies on rodents, the results of which were detailed in the journal Science, revealed another disturbing side of cosmic travel. It turned out that long-term exposure to heavy ions leads to the degradation of synaptic connections in the hippocampus, the part of the brain responsible for learning and memory. This poses a critical question for scientists. Will the Artemis II crew be able to make complex decisions at the culminating moment of the mission if their cognitive functions are suppressed by radiation influence? Imagine a situation where one must instantly react to a sensor failure or perform manual trajectory correction, and the brain of the astronaut experiences fog or slowed reaction. This is a risk that cannot be calculated in terrestrial simulators because the cumulative effect of microgravity, stress, and radiation on the human psyche remains one of the greatest mysteries of modern medicine. Psychology of isolation and the breakaway phenomenon. We often speak about physics, but the psychology of the Artemis II mission is no less complex. The Japan Aerospace Exploration Agency conducted a series of experiments in isolation chambers, simulating the conditions of flight to the moon. The results showed that the complete loss of visual contact with Earth as a three-dimensional body causes a state known as the breakaway phenomenon. This is a feeling of deep alienation and anxiety when the home planet turns into a small dot that can be covered by a thumb. Unlike astronauts on the International Space Station, who see Earth as a huge, detailed home, the Artemis II crew will be in a void where the nearest help is hundreds of thousands of kilometers away. Any micro-conflict inside the crew, or a psychological breakdown in the cramped space of the Orion cabin, could lead to errors in piloting. The conclusions of this section are unambiguous. We are sending people into an environment that is biologically hostile to their very existence. Every hour spent outside the magnetic field of Earth is a battle on the cellular level. The Artemis II mission is not only a test of metal and fire, it is a grand biological experiment where the price of knowledge is the health and lives of 4 people who dared to become the first inhabitants of deep space in the 21st century. We often perceive a journey to the moon as a straight line, but in the reality of deep space, it is a complex ballistic ballet where every second of engine operation determines the fate of the crew for millions of kilometers ahead. For the Artemis II mission, navigation is not just finding a path, it is a constant struggle with the invisible but relentless forces of gravity from Earth and the moon. The risk here lies not in the breakdown of iron, but in the very mathematics of orbital mechanics, which does not forgive errors even in tenths of a percent. Free return trajectory, a rescue ring or a gravitational cage? The basis of the safety of Artemis II is the so-called free return trajectory. This is a brilliant engineering solution that allows the ship to return to Earth even if its main engine completely fails after setting out on the path to the moon. The ship is launched in such a way that it loops around the far side of the moon and under the influence of its gravity, like a giant sling, is directed back to our planet. However, ballisticians from the Jet Propulsion Laboratory warn, this trajectory is a narrow corridor. If during the trans-lunar injection maneuver, the moment when the second stage of the rocket accelerates Orion to a speed of 11,000 meters per second, the engine works even 2 seconds longer. The perigee, the closest point to Earth, during return will shift beyond the atmosphere. The astronauts will fly past Earth and go into an infinite orbit around the Sun. If the engine shuts down too early, the entry angle into the atmosphere will be too steep, and the ship will simply burn up from overloads that will exceed 30 G units. We trust the lives of 4 people to the precision of sensors that must measure speed with an accuracy of centimeters per second. 34 minutes of absolute solitude. The most intense moment of navigation will occur when Orion hides behind the disk of the moon. This is territory where absolute radio silence reigns. The moon, having a mass of 73 quintillion tons, becomes an impenetrable shield for any signals from Earth. For 34 minutes, the Artemis II crew will be cut off from all of humanity. During this time, the ship must perform critically important orientation maneuvers, relying exclusively on its onboard computers and star trackers. If a software failure or mechanical jamming of one of the 32 maneuvering engines occurs during this period, Earth will not be able to send a command to fix the situation. The astronauts will remain alone with the problem in total darkness 800,000 kilometers from home. This is the moment of truth for the autonomy of the Orion systems, which have never before passed such an exam with humans on board. Deep space network and signal delay. Even outside the shadow of the moon, communication remains a challenge. The National Aeronautics and Space Administration uses the Deep Space Network, consisting of giant antennas in California, Spain, and Australia. However, physics limits the speed of information transmission to the speed of light. The signal delay in both directions is approximately 3 seconds. In a situation where the ship is moving at a speed of several kilometers per second, 3 seconds is an eternity. If an emergency situation arises during a critical phase of flight, the Mission Control Center in Houston will see data about it only when the event has already occurred. The astronauts must be ready to act as an independent unit, making decisions upon which their survival depends without waiting for confirmation from Earth. This requires from them not only technical knowledge, but also superhuman calm and confidence. Micrometeoroids, invisible shrapnel of deep space. Another factor that ballisticians consider when calculating risks is space debris and micrometeoroids. Unlike low Earth orbit, where debris is tracked by radars, in deep space we encounter natural micrometeoroids flying at a speed of over 30 kilometers per second. An impact from a particle the size of a grain of sand into the Orion porthole or into a fuel line of the service module could lead to instant depressurization or explosion. Although the ship has protective shields, they are designed only for a certain threshold of energy. Flight to the moon is a lottery where every hour spent in the void increases the probability of a fatal collision. We must understand that the ballistics of Artemis II are not just numbers on paper. They are a fragile balance between the laws of Newton and the unpredictability of the cosmic environment. Every point on the flight trajectory is a potential trap, and exiting it requires mathematical perfection from the crew and ground services. We conclude our deep analysis of the Artemis II mission, but the real story is only beginning. This expedition is not just a technical report or another step in space exploration. It is a moment when humanity again dares to go beyond its biological and planetary cradle, taking upon itself the burden of incredible risks. And if we look at this through the prism of philosophy and history, we will see that Artemis II is a manifesto of our will to live and to know. The overview effect and Nietzschean philosophy in space. When the astronauts of the mission, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, look back and see Earth as a small, fragile blue dot, they will experience what psychologists call the overview effect. This is a deep realization of the unity of all life and the fragility of our common home. However, in the context of Artemis II, this experience takes on a Nietzschean color. Friedrich Nietzsche wrote about the will to power as the will to self-overcoming. Man is a bridge between the animal and the overman. The Artemis II mission is that very bridge. We consciously go to the risk of the death of 4 people. We spend billions of dollars. We fight radiation and vacuum, not just for the sake of lunar soil samples. We do it to prove to ourselves that we are capable of overcoming our own biological limits. This is an act of stoicism in the face of the boundless universe, where we recognize danger but do not allow it to stop our forward motion. From Artemis to Mars, strategic necessity. The scientific significance of this mission is hard to overestimate. The success of Artemis II opens the doors for Artemis III, the first landing of a human on the south pole of the moon, where ice supplies are kept in the eternal shadow of craters. But the final goal is even more ambitious. It is the construction of the Gateway Orbital Station, the first permanent outpost of humanity in deep space. According to official plans of the European Space Agency and the National Aeronautics and Space Administration, the experience gained during the resolution of problems with the Orion heat shield and radiation protection will become the foundation for a flight to Mars in the 2030s. Artemis II is a proving ground where we test our right to be called a multiplanetary species. Without this risky step, we will forever remain hostages of one planet, vulnerable to any global catastrophe, from asteroids to climate change. It may seem that events 800,000 kilometers from Earth do not concern our daily life, but that is a mistake. Technologies created for the survival of the Artemis II crew are already changing our world today. New methods of water purification, ultralight and strong materials, advanced artificial intelligence algorithms for autonomous navigation. All of this becomes part of our medicine, energy, and everyday life. However, the most important thing is inspiration. We live in an era of great challenges and doubts. The Artemis II mission reminds us that humanity is capable of majestic achievements when it unites for a common goal. 4 astronauts on top of the most powerful rocket in history is a symbol of our collective courage. We have analyzed every screw, every law of physics, and every failure scenario of this mission. We have seen how thin the line is between success and catastrophe, but it is precisely this line that makes us human. We go into the darkness not because we are not afraid, but because our striving for the light of knowledge is stronger than any fear. Thank you for being with us on this journey through the Artemis 2 scenario. How do you think are such colossal risks justified for the sake of exploring the moon? Is humanity truly ready to become a cosmic species, or should we have focused on solving problems here on Earth? Write your opinion in the comments. We will definitely read every review. Give a like if you enjoy deep scientific documentaries, and subscribe to the channel so as not to miss the next episodes of our exploration of the universe. Ahead are new horizons, and we will definitely reach them. See you in the future.